This is a reproduction of a lecture given in the Seychelles in February 2016. Now, I will tell you about some aspects of tropical meteorology with emphasis on inversion and distribution of precipitation and orography on fine scales. Now, I will use this opportunity to draw your attention to this textbook, which is free of charge on the internet. And I would like to mention that this has been collected by Janman Bao and myself, and we have had some contributions from the European Center, from Kellen, and from Baode in Shanghai. Now, the area of the tropics it's a place where we have weak horizontal gradients, we have weak Coriolis force, weak horizontal temperature gradients, and horizontal pressure gradients are also weak. And why are these gradients weak? It's because there are not strong gradients in the incoming solar radiation, which is the primary source of energy in this area. In fact, we can define the tropics, and some people do, as the area where the sun is at the top of your head at least one day every year, reaching from the equator and up to 23.5 degrees north and south. Now, another way to look at the globe and the tropics is to identify areas of surplus and deficit in the radiation budget. There is a great surplus around the equator and great deficit. The atmosphere loses much more energy at high latitudes than it does gain from the sun, and the incoming and outgoing radiation, they balance each other at points which are somewhat further north than the Tropic of Cancer and Capricorn. Now, another way to look at the tropics is to look at the dynamics, the wind fields. We have easterly winds blowing in the boundary layer, bringing moisture to a convergence zone between the northern hemisphere trade winds and the southern hemisphere trade winds, and this convergence zone oscillates back and forth, up and north. Now, let's move on to the global energy balance. Most of you know this figure. It is an overview of the energy balance. We have the energy coming in from the sun. Only about half of it reaches the surface of the Earth. The rest is reflected before it reaches down to the surface. And we have substantial transport of energy in the long wave range, away from the surface of the Earth and back to the surface from the atmosphere. Now we have two elements here. As you remember, energy is not only transported by radiation but also by advection, and we have thermals giving rise to upward motion of energy, upward transport of energy, and we also have substantial amount of energy being transported by water vapor through the evaporation at the surface and release of latent heat in clouds. This is how the atmosphere would look like in radiative equilibrium if there was no transport by convection or advection. And if we add to this another curve that shows us how the dry adiabatic atmosphere would look like, we see that at the upper and most levels of the troposphere, the adiabatic atmosphere is much warmer than the atmosphere radiative equilibrium. And if we draw a third line showing the temperature profile with a lapse rate of 6.5 Kelvin per kilometer, which is close to reality in the troposphere, we see that this transport of heat is contributing to giving much warmer atmosphere at middle and upper tropospheric levels, while here close to the surface the convection and transport of energy through moisture is contributing to cooling down the atmosphere compared to the radiative equilibrium. So we have net gain here in the tropics and net loss here, and we do have much warmer air mass in the troposphere at low levels than at high levels. And this gives rise to a high at middle to upper tropospheric levels, and compared to an upper low at high levels. And this is how the average pressure field looks like. This is a long-term time average, showing that we have a relatively flat high at 300 millibars in the tropics, and low at the high north and high very low latitudes, and a strong gradient in the westerlies. Now, and this gives rise to the pressure gradient force, another way of showing that at high levels, high tropospheric levels. Now, let's take a look at the vertical structure. Here we have an example of a sounding from St. Helena in tropical South Atlantic. In the free troposphere, we have a lapse rate not far from the wet adiabatic lapse rate, and in the inside the boundary layer, the atmosphere is conditionally unstable. While here, in between these two air masses, we have an inversion, and this inversion is very, very common at low latitudes. It is present most of the time above the subtropical heights in the north and in the south, and below the inversion we have advection of by the trade winds of vapor towards the convergence zone, where the inversion has been broken by the extremely strong convergence. At the upper levels we have transport away from the convergence zone to the north and to the south. Now let's look at the vertical sections in the Atlantic. Here we have the subtropical high, and with the westerlies to the north and the trade winds to the south, and we make a cross section along this black line here and see how this the vertical movements, they change with the season. This is schematic through this vertical section. We have a strong inversion inside the subtropical high, while in the tropical convergence zone we don't have any inversion. We just have very, very strong and deep convection. This is how it looks like in a long-term mean. We have rising motion here to the south, and sinking motion inside the subtropical heights. And this is January, February, March. It moves, the whole system moves slowly to the north. And here we take a big step in April and continue to move to the north. And to the left, to the far south, we see the southern hemisphere subtropical high appearing, while the northern subtropical high disappears in our cross section. And in the summer, the intertropical convergence zone with a maximum rising motion reaches its maximum northerly position in July, August, and starts to retreat here in September. So does the subtropical southern hemisphere high, and again in October, November, and December we get the northern hemisphere subtropical high with the sinking motion coming in again.